going to try to do 5 basic examples of contour integrals in 5 minutes. And I'm going to be using Cauchy's theorem, Cauchy's integral formula, and parameterization to do this. So my first example here is of this curve. It goes from 0 to 2 plus I in this direction. This is not a closed loop, so I can't use Cauchy's theorem or Cauchy's integral formula, so I'm going to parameterize it. And I can do that by setting gamma of t equal to, how about 2t plus ti, where t goes between 0 and 1, right? When t equals 0, I'm going to be at the origin. When t equals 1, I'm going to be where I want to go. So this integral is going to be the integral from 0 to 1, because that's what t goes from, 3 times, right, this is what I want my z to be equal to. Z is now equal to 2t plus ti times the derivative of this, which is just 2 plus I. Right, because the derivative of 2t is t, the derivative of ti is I, and then just do dt. And now, essentially, you just do this the way you do it in calculus. Here's a constant, here's a constant. You do 3 times 2 plus I times the integral of 0 to 1, 2t plus ti. In fact, let's even do this. 2, factor out the t. 2 plus I t dt, which equals 3 times 2 plus I squared times 1/2 t squared evaluated from 1 to 0, which equals 3/2 times 2 plus I squared. That's the first example, and I use parameterization. Second example is I'm going to do an integral over this closed curve, and it's z squared. Now, I'm going to assume that this is really kind of a nice curve and is homotopic to basically anything I want in a very nice way with continuous second partials. But if this is true, hey, notice that this thing is holomorphic. The integrand is holomorphic everywhere. That's really the question: is where is the integrand holomorphic? It's holomorphic everywhere. It's holomorphic on the interior. So that means that it's going to be that this curve is homotopic to this point. And everything's homomorphic. Sorry, homotopic. And by the way, the homotopic part doesn't have anything to do with the z squared. I misspoke. But since this is holomorphic everywhere, that means I can basically contract this down to a point and take the integral over that, the integral of the green thing, z squared dz. But this is just a single point. If you integrate over a single point, you get 0. So essentially, I'm going to use Cauchy's theorem to get this. Over here, let's play the same game. I can contract the circle down to a point. E to z is holomorphic everywhere, so this thing is equal to the integral over the green curve, which is just a point, so I know that that integral is equal to 0. So again, by Cauchy's theorem, I can do this really easily. The integral is just 0. So I'm down to 2, and I've got a minute and a half to do it. We'll see what happens. So here, this should be dz and dz. Here I have a little problem, because the integrand is not holomorphic everywhere in here. In particular, at this green I divide by 0. Well, this is a classic Cauchy's integral formula problem. And this just says, as long as the numerator is holomorphic everywhere within inside the curve, the circle, then I can just say that this thing is equal to 2 pi I, right? As long as everything else kind of works out nicely. It's going to be equal to 2 pi I, z to the 17th, evaluated at I, which equals 2 pi I times I to the 17th, which equals 2 pi I times I equals negative 2 pi. Okay, last one, and I've got 30 seconds to do it, no problem. Okay, so here I have a very similar situation, except now the problem point is at 3i. But 3i is outside of the region I'm integrating, so this integrand is holomorphic everywhere in here, which means that I could contract here. So since the integrand is holomorphic everywhere on the inside, I can just use Cauchy's theorem to get that this thing is equal to the integral of whatever it is of this thing, and that's just a point, so that's going to equal 0. And we're done.